Thank you. Right. This is what Danny's talking about. You can pass this round. Have a look at that. Don't put it in your tea. No, it's a different kind of tea. I've got a question. Does anybody actually recognize me for anything else, or is everybody new to me?
I kind of feel I do recognize you, but...
Somewhere. Okay, it was a bad dream. Fine. So, my name is Daniel Tirkel. I'm the director of Soil Ecology Laboratory, which is a little lab of geeks and nerds down in Hampshire. And we focus on helping farmers go towards their regeneration goals. And is there anybody here who would call themselves a regenerative farmer? Okay, we've got one. Great. So if we think about being a regenerative farmer, really people go towards that direction because they usually get squeezed on one side with all sorts of monetary things. And then on the other side, you want to increase the functionality of your soil so that you don't get hit with all sorts of problems that nature throws at you. Is that roughly about right? That will be the motivation to go regenerative. And now we've got this really interesting period in our farming history in the UK where we're starting to see these sort of nature pressures, like last 2 years were very wet and this year was very dry, and then in 2022 was another dry year, so that's becoming more and more common. And then on the other side, the government's decided, yeah, we're just going to pull all of the subsidies and leave you with nothing. Is that about correct as well? Okay, there's more nods there. Thank you. So what we've been doing, we've been following in the footsteps of Dr. Elaine Ingham, who's an American researcher, and since the 80s she's been blabbing about compost and compost extract, but not just from the perspective of let's have some nutrition and put it back under the soil, but let's actually use it to grow out beneficial microbes. Now, why would she want to do that? So if we are thinking of creating that resiliency, we're starting from the soil, then we need to think about what functions can that soil provide us. And if we think of the soil function and the improvement that we can actually gain, are we going to be looking at the mineral part of that soil and trying to improve that? So we know that with our mechanical implements, we can do something in the short term. So we can break up compaction, we can increase the tilth of the soil. So that's the physical. We know that we can maybe add some calcium to improve the calcium to magnesium ratio and loosen up some tight soils, or maybe increase the magnesium and actually tighten up some loose soils. So that's the chemical side. But then the real improvement comes when we actually start looking at the biology. And why is the biology important? And so we've got a historian here, but not a paleontologist. But the thing I like to think about is that plants, and obviously these are our crops as well, they started evolving about 650 million years ago. And when that was happening, when the terrestrial plants started colonizing land, microbes already had 1.5 billion years of head start of evolution. And so they sort of come to that land and they see, okay, well, there's this massive soup of organisms that we can maybe work with. And plants are in this unique position that they photosynthesize. So they can produce sugars out of pretty much thin air, right? Water, CO2, and they produce sugars. Microbes, apart from, certain microbes, obviously algae is a big group, but microbes on land don't necessarily are very good at that. Plants are much better at that. And so plants, okay, well, we're just gonna go and feed these microbes and see what we get in return. And what you get in return is everything. So microbes have the capacity of unlocking nutrients that plants can't. So plants can unlock soluble nutrients and exchangeable pool of nutrients, right? We know what those are. Every agronomist will be telling you about those. But microbes can access the total pool of nutrients. And then when you look at the maps, for instance, of phosphorus and potassium in the country, there is no farm in the country that lacks any of those. Like, there is none. Like, every farm in the country has got plenty of that for years, for hundreds of years to come. So it's not about the lack of these nutrients, it's about the access to those nutrients. And it's the activity of those microbes that can do that. And then there are other functions that I will talk about when I actually turn on the presentation. But all I'm just trying to say is this. If we're looking to improve that function of our soils, then we're not necessarily only looking at the chemical and the physical properties. It would be good to start thinking of those biological properties. But far too often, we hear about these biological things as an afterthought or as some sort of a vague promise. What I want to tell you is that we can use these things as a tool, just like anything else that you use as a tool, right? You use your ammonium nitrate, your urea as a tool. You use your plow or a no-till implement as a tool. And you can use biology as a tool. But we need to be able to do something to use something that we can trust, right? So I brought you a little presentation, and this thing, if I can get it to work, I'm gonna just be hunching down to actually do something with it, but hey ho, that's us. We do products testing and training. And the question is about compost extract, because, you know, again, Elaine Ingham said, you know, use good compost and then make compost extract, because you're never going to make enough compost to spread it on your lands to have enough biology. But if you make an extract, you can make it more efficient. And then Dr. David Johnson came up with this Johnson Soup bioreactor, and farmers started to put together those. Does anybody have got one of those? No? No. Okay. This is basically where the salesman in me is going to come and say, just buy that. But that's going to come later, okay? So the thing is this. We as a lab, we could have just basically said, we're just going to haul ourselves up in the lab and just basically put little pots everywhere and just basically, you know, have a little wheat plant here and a little barley plant there and, you know, some oilseed rape there, and basically just do everything in the lab in little controlled conditions. You know, I'll be spoon feeding them everything that they need, and I'm going to present you with results and say, buy this or buy that, right? I don't like that, and you don't like that. And so we've always been doing stuff in the field, and I'm going to talk about this in a second, and about this as well. So 2021, that's spring barley. After a layer of compost, green waste compost, was added onto the field, there's no chemicals used, just water on the control. This is yield in tons per hectare. Then there's a 3 times spray of biology, and then the conventional with, I can't remember how many, 120 kilograms, I think, on the spring barley. And so those graphs, you know, doesn't really say much, but when you actually look at the numbers, just the application of biology in the context of having that nutrition resource that normally would be sitting and decomposing over time, the addition of biology actually improved the yield by 40%. So that's a number. You can put that number on your spreadsheet, and you can know actually what your yield is going to be worth to you, right? In 2022, Mikey Barton in Scotland did a trial where the vertical strips, this is 1 hectare on pasture, the vertical strips represent the treatment of the soil. So grazed off, sprayed off, plowed, ripped, and controlled. And then you kind of can make out horizontal strips. And the bottom strip got that. The next strip got 50 kilograms of nitrogen per hectare. Then the third strip got some seaweed extract, and then the control. 2022 was a drought year, and this is where Mikey came to us and said, everything is flopping over apart from the biology. We don't know why. That was the first time we actually saw that. But the result was that the nitrogen gave about 49% increase in biomass over control, because Mikey was measuring with a plate meter. The biology side gave about 29, I can't remember exactly how many it was. And then the seaweed extract was about 14. So you can put that on your spreadsheet. You can basically have, a number. This is the value to me of adding the biology to it, right? What was really interesting though is the field, the part of that trial which was sprayed off with glyphosate, that actually, the NPK, the seaweed didn't control. There was no difference in biomass. And the biology actually outperformed it. So the question is why? And we then did some other experiments and also some literature review to see, and we've got some hypotheses as to why. And we came back to this field. And this was a Haney test that we did on that field, on that glyphosated strip, where all of the metrics the next year, without any further applications of anything, were up against the control and against the NPK and against the seaweed. This is a tool that you can make on your farm if you know how to do that, and then you can start applying it and you can have a financial benefit. Next, 2023, Charlie McLaren. He's a good friend and semi-retired agronomist. I call him the cow whisperer. He just can look across your field of your cows and can tell you what's wrong. And Charlie wanted to help a sheep farmer to relieve compaction on his soil. And so he thought, let's just use some Goop as well as an experiment. They chose a number of seeds to drill into that field, and a lot of them were taprooted plants so that they can break that compaction. And they split it into 2 parts, 10 acres without any Goop, 10 acres with some Goop. And he used a protocol made by another dairy farmer called Tom Gregory, who basically used 50 ml of that with 500 ml of water with 10 kilograms of small seeds per acre. And so that's what Charlie did. And then he waited for some rain. He then got the sheep to graze off the whole field to 3 millimeters, manure it properly, and then they drilled it, and that was early June. Towards the end of July, they baled up the whole thing. They got 40 bales of the control, 45 bales of the treatment. You can put that on the spreadsheet. 2024, Sam Carey, Welsh dairy farmer. He got himself a grant just to buy as much Goop as he could, so he could just blanket the whole thing. And he's asking me, how much do I put per hectare? And I said, well, we have used as a spray, we used 14 liters, but we don't really know what is the economical number. It could be less. So he went from 2 liters to 12. And basically, they didn't measure biomass, but they had a researcher from, I always butcher this, thank you, university, come in and measure stuff 7 months later. So then they went and measured all sorts of things 7 months later in the soil. What they found, for instance, is that nitrogen release was not dose dependent, but potassium release was dose dependent. So the more biology you actually applied, he actually had a better release of potassium from the soil into the plants. So that's recorded, and that's something that you can look up and you can put in a spreadsheet. And then this year, it's not the only one from this year. And I'm not missing, this is 2024. But this year, Ed Gallia, spring barley in Dorset, drought year. So he came to us in February to learn to use the microscope, because we do that. And the same month, he purchased 28 liters of the Goop, went away, and then I waited with bated breath for months and months and months until the harvest happened. But before he even went drilling, I said to him, are you going to use pre-emergence herbicide? And he said, well, yes, obviously. And I said, what's the point of me selling to you biology if you're going to kill it? And he says, well, my agronomist is going to cry, but let's agree a split trial. And so that's what they did. And there are 2 fields that were complete in the trial. So one of the treatments was the complete treatment. So you had the addition of the biology onto the seeds and no pre-emergent spray. Then you had the addition of the biology to the seed and the pre-emergent spray, and then the control, just a typical system without any biology and with the pre-emergent sprays. And the result is there is a half a ton extra where the seeds were coated in biology and there was no pre-emergent spray, and less than 1/4 of a ton extra if there was a pre-emergent spray. So what does it tell us? Because if you recall, we saw this here as well. Glyphosated strip was underperforming, and only addition of biology actually helped to increase that yield, that biomass. And we do have a number of hypotheses, and there's literature review that we've done as well on a limited basis. We've done a test. This was the most expensive wheat on 3 square meters that we've done in controlled conditions, right? I think I spent like £5,000 on testing. And we found that the addition of biology actually slowed down the decomposition of glyphosate, not sped it up. It slowed it down. And we don't know why. And one of the hypotheses is that it actually just locks it. The production of fulvic acid, the humic acid, just like you could basically, like Nicole Masters says, add the humics to your glyphosate in the tank. It's potentially locking it. There still was a degrading action of glyphosate, just like in the control, but it was slower. It was actually statistically significant. So the thing is that we're using this popular herbicide, and we're using this especially in a regenerative system, specifically to terminate the cover crop, which is supposed to give us nutrition and save us on fertilizer, right? But it also acts as an antimicrobial agent. And especially that pre-emergent spray sterilizes everything, which means that you spent the money on the cover crop, it grew throughout all winter, and then you terminate it with glyphosate, and then you have to wait for the release up to 3 months. By that time, your crop is pretty much ready to go. So how do we sort of regain that control over that? That's the question. Without jeopardizing anything else, without risking blackgrass, without having just a massive loss to weeds, right? And so those are very good questions, which we really don't have answers to, but we do have some hints and hunches towards that. So first of all, there are some agronomists in the country that will tell you, terminate your cover crop in early January, and lose 3 months of growth potentially, right? Because they've noticed that they terminate with the glyphosate and they don't really get any decomposition, which means that you still have a standing dead cover crop by the time you're drilling. And so, you need to maybe turn it in, but you're supposed to be no-till. So how do we sort of balance that out? But if we were to allow the cover crop to grow as close as possible to drilling, terminate it then, spray biology, fresh biology, 2 days later, 3 days later, so that the microbes that you grew in compost, which are happy saprophytes, they just love to decompose stuff. That's what they do, 24/7. They'll basically jump on that cover crop and they'll start decomposing it faster. And then the protozoa nematodes will actually start putting the nutrition to your actual cash crop, right? That's a tool. Again, it's a tool. Yes?
If you keep spraying, we've sprayed our fields for probably 20 years with glyphosate.
Yeah.
Will the soil learn how to deal with that glyphosate better? So some of the microbes would be maybe destroying some microbes, but propagating others because of the glyphosate. And would it break down quicker the more we use glyphosate?
Do you know what? that is the best question I have heard in probably this year, if not in the last couple of years.
Thanks very much.
Good, Pat. Couple more. So, yes, like that's not resounding yes. Okay, I'll give you that resounding yes. I've got a little bit of a problem with that resounding yes, and I'll tell you why. So, we have a system where we will be adding this chemical, that chemical, this chemical, that chemical, and then we're going to be reducing the height of the plant with chlormequat usually, right? And then we're going to be feeding it synthetic fertilizer, right? And so the microbes in the soil are going to be responding to all of that, not just the glyphosate, all of it. And microbial community are very elastic. They basically will adapt to anything that you give them. So if I'm telling you that you could be using a microbial community as a tool to help your plants grow and actually increase your bottom line by reducing certain inputs and then replacing it with the biology and even stuff that you can make on your own on the farm without really any extra cost. If at the same time we're basically treating the soil with all of that and we're not allowing the natural interactions to happen between the plant and the microbiome, what you're doing is you're training your soil microbiome to simply deal with all of the disturbances. It's a war zone. And it's supposed to be a school. So yes, it will deal with it. There are plenty of glyphosate junkies in there. The first metabolic product of glyphosate decomposition is called AMPA, and it's more toxic than glyphosate itself. So yes, it will deal with that. Then we'll create AMPA. Then more microbes will die. Some others will have to come in and start decomposing AMPA. And that's literally why we have seen glyphosate residues in any soil, basically. It's a very expensive test, by the way. So what's really interesting is to also keep in mind that the same thing, same mechanism, is what we've been seeing in how we actually generate the sort of microbes that you want to have in your soils. And if we start considering these things as tools, and we can start shifting the mindset from just using the crop protection tools that we're used to, and we start using these things as tools, we can actually have something that's going to replace these other tools. And at the same time, you're going to have less runoff. You're going to have less hippies crying that you're poisoning them. You're going to have more money in the bank because you're going to be controlling that. So, you know, another war happens and the fertilizer goes up like this and you're going to like, I don't care. We probably would want that. Welcome it at least. So this is such an important question because not only the answer is that yes, your microbes will do that, but if you were to flip that on its head, you can actually consider, okay, well, if they can do that, what can I teach them to do? And I'm going to show you something today that is really like that. But I'm going to continue with this presentation for now.
Is the usage of glyphosate not completely in contradiction with regenerative farming?
Because I can't give you a solution today, right? I can give you almost a full solution for everything else.
You kill plants.
Yes.
And plants and soil and life in the soil is a good match.
Yep.
Is it therefore not advisable from a regenerative farming point of view to have plants all the time throughout the year?
Yes.
Because they are trapping, as you rightly say, for making
sugars.
Yep. And invested in the leaf material,
yep,
but also in exudates.
Yep.
That feed the life in the soil.
That's exactly right.
If you kill with your glyphosate all the plants,
yep,
then the life in the soil is starved of nutrients.
I've got two things to say. First of all, I agree with you, and I'm going to call that a disturbance. So glyphosate is a disturbance to the system. Plowing is a disturbance to the system, right? Nature basically usually just grows, stuff grows, and then maybe a fire comes. That's a disturbance, right? But we create the disturbance. As farmers, we have to. Like, look at a potato farmer, right? You have to have that disturbance to even just pull them from the ground, right? It's just what we do. So I call this a disturbance, right? It just happens because we do that. Now, the time that basically I see that the farmer is wanting to use glyphosate, a conventional farmer, may I just add, is, okay, well, I need to switch from growing a cover crop, and I want that nutrition from that cover crop, and I have to stop it from growing somehow, and I have to start decomposing it somehow, so I can then put my cash crop into it, because that's basically what I want to do, right? So most farmers will have that outlook on how they grow things, most. And so I am a sort of person that, you know, I want farmers to be able to take small steps, not necessarily just, you know, go full hog, because you rarely can do that. We only have one crop per season, right? We lose that crop, we're in trouble. So if we agree that a farmer has put in a cover crop, is now terminating it, and has to make a choice, Are we going to flip that soil, or are we going to use the glyphosate? And if the farmer believes that flipping of that soil is not good because we're going regenerative and we want to avoid that disturbance, so then the obvious choice is going to be glyphosate. What I'm trying to say is this. If we do go for that choice, first of all, let's reduce the amount with something like humic acid in the tank, because that has been shown to help. When you reduce that amount, you actually start reducing the negative effect on the microbiome. It was very hard for me to find literature on the effect of glyphosate on beneficial microbes. It was very hard to find. And I found one paper which is actually quite interesting. It was done on soy in America, which is obviously a big economical crop over there. And soy is a legume, which means that it's now dependent on those nitrogen-fixing rhizobia. And what they found was that anything above 1.5 liters of glyphosate per hectare had a detrimental effect on the nitrogen fixers in those nodules, and you could lose up to 50% of the crop because of the glyphosate affecting the microbes in the nodules, right? So if you were to reduce your glyphosate amount below 1.5, closer to 1 liter per hectare, you're at least reducing that disturbance. So that's one thing. Second thing is, don't use pre-em sprays if you can, right? I've got a hard time telling Edgallia not to use pre-ems in winter, obviously, because that's where blackgrass shines, right? It just goes, yeah, no problem, mate. I'm just gonna grow here. You do your thing. I'm just gonna grow here, right? It's gonna bring the ergot with me as well. So I can't tell him to do it then, but I can tell him to do it in the spring. And that's what I'm going to advise everybody who uses this product in the spring. Not to use glyphosate as a pre-emergent spray, not to use any pre-emergent sprays. Just skip that. Don't kill your biology. Don't add to that disturbance. Now, to go deeper into your question and your statement, pretty much, I agree with you because, for instance, I've got a good friend who's an organic farmer on 600 acres in Scotland, and he's a mechanical engineer, and he's put himself a mower in the front of his tractor, a roller crimper on the back of his tractor. Sorry, not a roller crimper, a shallow plow in the back of his tractor. He mows his cover crop, which is this big, and then he flips it by 10 centimeters. And that's his system. I have not measured the loss of carbon there. I have not measured the loss of carbon after using glyphosate. That's something that I would love to do. Because this is really the question, right? What is the amount of diesel we use in both cases? What is the gain or the loss of carbon in the soil? Because net zero is coming, and then there's all these, you know, carbon cowboys are telling you, oh, you're going to make a fortune because you're going to be storing soil in carbon and stuff, right? So I think this is something that, you know, we have to look closely and really, as clusters like this, investigate, run those trials. You know, this is not something that's going to be terribly expensive if you do a strip here and a strip there. So that's on that. I'm just going to continue for the sake of time. Just say Ed got that result. And by the way, Ed got that result with twice this amount per hectare, 400 mil. We've done a little, I said to you, we don't do a lot of lab stuff, but we do. So Johnny, or Dr. Jonathan Furs, he did this 10th trial this year as well on spring barley. And adding just biology, the red tabs, the red bars, this is dry matter after drying, okay? This is barley, 6 weeks barley. And this is biomass, above ground biomass. And the gain from adding biology to those seeds after 6 weeks was 30%. Controlled trials, so ignore it. But you know, we've seen it now in the field and in the controlled conditions. I'm going to tell you about this later. But there's another reason, you know, why consider using these things as a tool. This year was a drought year. That thing in the top left-hand corner, salicylic acid, is responsible for drought resilience. This is why we've seen in 2022 those plants standing up where everything else was flopping over. This is why customers of ours on the retail side say, oh, I have to water my garden less. We don't know why. Well, we do. Salicylic acid increased after 3 months in soil with wheat, after several applications of biology, by 70 times. Not 3, not 5%, 70 times increase. And that's why biology can be considered a tool when nature is putting pressure on us, okay? There's a flip side to that as well. You want to go no-till, but the soil is tight and there's compaction layers. The one thing we don't do in this country, nobody really has explored properly, is putting a tank on the back of a ripper and just dripping it as you're ripping your soil, so that it doesn't recompact. I don't have the details on that. Unfortunately, people don't do that in the UK. I've got one good friend in Jersey who's done it before potatoes. He swears by it. I've got a very good friend whose data I've seen on a little plot she's done by hand at the Royal Delft Botanical Gardens in the Netherlands, where she literally measured 5 compaction layers within 65 centimeters, and she dug through by hand 4 plots 7 by 3 meters. She's great, Tanya. I love her. And the thing is that she grew Jerusalem artichokes, and the controls recompacted during this growing season. But where she added biology in the profile, it didn't. So I'm not telling you that this is a solution. I'm telling you that there is hope to control it to an extent. I know the state of the soils across the country. I know that if you're lucky, you're sitting on soil, and a lot of people are just sitting on outcrops of something, right? On our farm, we're sitting on chalk. And basically, you know, if we're lucky, we've got 30 centimeters, right? So there is that. Exopolysaccharide production, heavy metal resistance, insecticide agents. Worried about root feeding nematodes, maybe? This is, after seeing the DNA results about drought, Adam Swan, our head geek, he spent hundreds of pounds of his own money, literally. And he bought aerometers, tensiometers, really expensive tools to actually measure water loss from soils. And then he set up 3 pots aside, treatment, control, put 6 wheat plants in each pot in a neat little row. And then he added 1.5 milliliters of this per square meter in the treatment. 1.5, like this much, okay? And measured the loss of water over 10 days. There's a 7% difference in 10 days in the whole profile of that soil, not even just in the root zone. So that's a tool. What else do I want to show you in this? Aha, yes, of course. So I'm going to make a little compost extract for you. This is something that you can do. This is something, you know, that you've heard about. It's like, let's put a Johnson-Su bioreactor and then forget about this for a year and then come back to it and then make an extract out of it and then do something with it, right? Most farmers, because this is the most economical thing to do, coat their seeds. Just don't kill them afterwards with that pre-em, okay? Then you'll be able to use it as a tool to its full advantage. Ask other farmers that have done it. Hutchinson's agronomy, they've got people dedicated to it. Dan Livingstone, another agronomist, DJI agronomy, they've got farmers, they've got basically farmers putting those things all across the country. And if you can't be bothered, you don't want to spend a year of your life, 2 years of your life doing that, buy this, it's inexpensive, per hectare, and you'll be able to start playing with it. But again, you can do this yourself. And do I do this first? Yeah, why not? You really want a practical presentation, don't you? So, I'm going to move this so I don't splash my computer completely. But I'm going to come back to this because this is really cool. I've got some compost here, but some very special compost. And this relates to that. And I've got now 2 buckets. I've already put 10 liters of water in this. And I'm going to put in a few liters of compost. I'll tell you what it is made out of, by the way, and you will not guess. Plop. My very sophisticated tool for extraction that you can get for 60 quid on Amazon. What's the setting? 1. Lowest setting. And it's not working. Obviously. That's the best thing to happen. No, it's broken. Sorry. Imagine I'm doing this. You would do that for about 30 to 45 seconds on the lowest setting. So you would basically go through that, create that whirlpool in the bucket, okay? I've put about 5 liters of compost. That 5 liters of compost would equate to about 2 liters of that, of this particular compost. A liter of regular Johnson-Su. And that means that you would get, you know, from that amount, you would get your 1 hectare test site for seed coating from this amount. That's enough to do your seed coating. So unfortunately, we're going to do that. There is a pond filter here that I would just basically pour this through the pond filter so that you capture all the big bits and then you're left with something that is under 400 microns in size, which means that you can use that as a spray. You just have to remove filters from your sprayer and put larger nozzles. Anything 1 millimeters or larger, basically. So we've done it with a typical chafer sprayer, actually. So I'm sorry I can't give you a nice whirly presentation because my thing just decided not to work.
What's the whirling actually doing? Why is it making it different from just? Well, it's just dissolved in it. Is it doing anything else?
So this is compost. So this is compost, right? Yeah. And that means that the microbes are sitting on the surface of the organic matter, holding tight onto their dear lives. And then what I'm doing is I'm literally just persuading them to come off that organic matter. If I don't do that, they will not do that because they don't like to. And what we want to have is we want to have an extract that is rich in those microbes. When I also keep saying microbes, bacteria, fungi, protozoa, nematodes. Bacteria and fungi, they're usually responsible for decomposition in general in the soil. The protozoa, the nematodes, they actually cycle nutrients from the bacteria mostly. So if you think about the bacterium, it's a living organism, single cell living organism that really doesn't want to die. You want it to die so that its nutrients can go into your plant, right? So the bacteria is just, floating about, gathering nutrients from the environment, but it is in itself a micro-fertilizer bag, and somebody has to come along and open it. And so protozoa and nematodes do that job for you. There's only a small number of ways a plant can get food. And in natural ecosystems, it's not synthetic fertilizer, okay? So you can have the rhizophagy cycle where plants ingest bacteria, literally take them up into the roots, bombard them with oxygen radicals to open up the cell walls and suck up the nutrients. Then, by the way, they let some of them through, let them live inside the plants and do jobs in it, increase their population, and then send them into a different route and put them out into the root zone via a root hair that they've just created for that purpose. Root hairs are created because of the rhizophagy cycle. And so now a new colony is seeded in a different location that can start gathering nutrients, and the same cycle can happen again. You can have mycorrhizal fungi, which everybody knows about. You can have dark root septate fungi would grow in between the cell walls. You can have endophytic bacteria and fungi that live inside the plant and do jobs. And by the way, they also wait for the plant to die so they can start decomposing, and they're the first on the job site. And then you have the great majority of free-living microbes, bacteria and fungi. And you have to have the protozoa and the nematodes to consume them to be able to release those nutrients. And papers from back in the 70s basically showed that if you have a bunch of bacteria, nothing will happen. Your plants may get something from the rhizophagy cycle, but not a lot. But if you have amoeba or nematodes, within 6 hours, you're going to have 100% of that nitrogen from those bacteria going to your plant. And because your plant is producing sugars, putting them out into the root zone, feeding the microbes, they hang around the root zone. You can see that on the microscope. I can take a sample from your soil in between the rows of plants, and there will be nothing there. And I can take the same field, 5 centimeters next to it, take the whole plant, wash the roots in water, look at that sample, and it's going to be full of life. If you've maintained that life, that's of course, right? So, why is this thing actually quite special? So, this is fun. That's the last thing I'm going to be telling you today. So, if you're getting bored, I'm getting there. Hopefully, before I chucked it in there, you've taken note of the look of that compost, right? Any guesses what it was made of?
Grass? Grass?
Close? No banana. Coffee? Nowhere near.
Straw?
Yes, and only straw. And what's really interesting, we've been hypothesizing about this stuff for years, and we've managed to put together a prototype. This is that prototype. And we now have got other farmers putting together their prototypes so we can get more data. Because the hypothesis was, we need to increase the amount of nitrogen on farm for the farmer to be able to reduce the inputs coming from the outside. So if a farmer wants to go net zero, he wants to reduce the oxidation from the synthetic fertilizer, he wants to spend less on those synthetic fertilizer. What do we do on farm to be able to do that? Well, you can grow some legumes in your cover crop rotation, that's one thing. You can bring livestock onto your farm, you can have a mixed farm. Not everybody can do that, and we are in Norfolk, right? And there's plenty of farms that are not mixed farms here. So, Lincolnshire, same thing. So we end up in a situation where we've got these very limited options of what we can do to actually create more nitrogen on farm. And so when I think of microbes as a tool, I think of nitrogen fixing bacteria that are free living if I'm not using legumes. But they need food, and they need a lot of food. And if I just count on my crop feeding them, maybe I'll get 20%, 20 kilograms per hectare, which is a tenth of what we need, right? Maybe a fifth if we think about the fact that it's actually going to be utilized better. But it's a small amount. And then at some point, it hit me. There was other sort of things that I've noticed, and you all have straw. Not this year, I know. But you all have straw, and straw is basically, it is cellulose, 60% cellulose and hemicellulose. And cellulose is a chain of glucose, sugar. So somebody has to break that chain to be able to get to that glucose. And there's plenty of those. You just have to give them the right conditions to do. And so what we did is we put 6 big Heston bales of straw, 8 foot, 3 by 3. Let rain do its thing. We just added a bit of this as a starter. Not a lot. I can't even remember if I put composting worms in it, but they were there. Within 13 months, because that's how long we left it there, we measured everything. So we weighed the original bales, we weighed the resulting material, we sent it for analysis, and we crunched the numbers. We got doubling of the nitrogen inside that straw from the starting point. The carbon to nitrogen ratio went from 87 to 1 to 16. In the second year, because that keeps decomposing, it went down to 10. 3.5% nitrogen. That's chicken manure levels. That's a fertilizer. Okay. Now, what got Adam really excited is this DNA analysis. That's from that compost. This actually, it wasn't our prototype. This came from James Argyle, another farmer, and we sent this for DNA analysis, and this is all of the stress adaptation. So that's a tool. So you can make that on farm. You can basically put bales of straw, put them somewhere in the corner of the farm, let it decompose. If you have some compost, put some compost extract on it to get it started, or ask us. We're now running a group of farmers that are replicating it. And so I've got more of the old straw compost, and I'll just send it to you. I'm not going to charge you for it if you participate in that. And so you've got all this stress adaptation, got some more in here as well, hormone production. That's all high, and that's specifically for wheat. Specifically for wheat. Those results wouldn't be that high for any other crop, which means that the straw compost has got a community of microbes that work specifically with wheat. Another thing that we actually saw, which put us on this trail, was we've got friends who do this in Israel, and so we asked them, go to the national parks and collect the soil from the rhizosphere of wheat that grows there for thousands of years. It's not a monocrop; it's a meadow, and wheat is growing there. So they did that in triplicates from 4 different locations. They sent that out for DNA analysis, and we got basically a very similar microbial profile in Israel, in the root zone of those naturally occurring wheat, and our straw compost. What does it tell you? We didn't carry anything to the UK. It's basically what they want to do. They literally want to help you. Yes?
So the auxins and gibberellins, we would always put growth regulators on.
Yeah.
To inhibit.
Stop it.
To stop it. Put blocks in.
Stop it.
Yeah. So.
Just don't do it.
Still do it.
Don't do it.
Don't do it.
Don't do it. Think about it logically. First of all, it's a convenience factor. Okay, I've got an easier job combining. Great. Maybe you might see a little bit of yield increase because you got less energy going to the straw, maybe to the thing. Well, that goes on the spreadsheet. That's important. Then somebody tells you, well, because it's lodging, right? Okay, well, why did those plants lodge? Do you know? It would be good to understand why does why do these plants actually do that? And that usually has to do with the wet field. And then there's an inhibition of production of lignin in the plant. When you actually solve the root cause, they won't lodge. So it's a practice. So you could actually replace your growth regulator with practice. And you've got a stronger plant. You've got taller straw, meaning that now you can actually produce more fertilizer on farm. Do you see where I'm going with this? And by the way, yes, chloromyquat is very easily decomposed by microbes in the soil. That's done. That's good. Anything else? I'm pretty much done with this, so you can ask questions. If you've got any, that is, because I talk too much.
The food web of Elaine Ingham, is that not referring to fungi?
Yes.
And could you elaborate on the different microbes there are?
Yep.
And what they release in terms of potash, nitrogen, maybe better than, say, the fungus.
So the basic soil food web, when we talk about that, we talk about bacteria, fungi, protozoa, nematodes. Mm-hmm. Release. That's a big word as well. I could talk about groups, but you can have all groups and then something might not get released.
I have heard a talk here in Norfolk where a farmer puts his soil under the microscope and identifies goodies and baddies.
Nick Padwick.
Yes.
Yes. Good friend of mine.
Yeah.
So we've gone way deeper, actually. The goodies and baddies, what Elaine would refer to is actually what's going in the direction of being waterlogged and anaerobic, actually. When you look at the test that Elaine provides, all of the groups that she talks about in terms of goodies and baddies, you can basically relate that to what's waterlogged and anaerobic and what's aerobic. And so on the fungal side, she uses the term oomycetes because these are water molds. So you start seeing the morphology of oomycetes, then you're going, okay, well, we're getting waterlogged and anaerobic. You're seeing more ciliates and rotifers, we're going waterlogged and anaerobic. You're starting to see spirochetes on the bacteria side and Vibrio, you're going waterlogged and anaerobic. You're seeing root-feeding nematodes, you're waterlogged and anaerobic. So that's the goodies and baddies, basically, side of things. There's also an in-between, by the way. Now, when it comes to your original question about, what stuff get, release, that is such a big question. If I wanted to simplify it, there's a certain level to which bacteria can do everything. And then above that level, in terms of complexity, they have they can't do that anymore, and now fungi step in and they outcompete them. And the best example of that is if you think of available organic matter that you've got to feed your soil with, straw, bacteria basically dominate because they can decompose cellulose. There's plenty of species of bacteria that can decompose cellulose. You put a wood chip on your soil, bacteria can't do anything with it. It's only the fungi. It's the original plastic of nature, by the way. I don't know if you know that. There was a time in eons of history of planet Earth where wood couldn't be decomposed. That's where coal comes from. Because wood couldn't be decomposed. And then fungi figured out how to decompose lignin. But bacteria can't do it. And so if you actually want to promote more fungi in your soil because you have heard that they can perform other functions, they can help with a lot of things in the soil, like buffer the calcium to magnesium ratio, like bring up more of the nutrients to the plants in more economical way than bacteria can do, then you actually need more lignin. And there's a good paper on that which looked at all possible materials available to farmers and how much nitrogen do you have to provide before that material can, before the microbes stop robbing your plants and actually start decomposing that that material. And poplar is actually one good example. So the bacteria and fungi, they will go for the mineral part of the soil, but they will first go for the organic part of the soil and basically look for stuff there. And it will continue decomposing whatever is in the organic layer until they turn it into a version of carbon they can't do anything with. That's humus. If anybody tells you about humic acid, fulvic acid, it's very hard to put a molecule, chemical formula on that molecule in terms of humics, because it's just a jumble of carbon. They can't use it as a resource. It's only a resource that you can put all sorts of stuff attached to it on the exchange sites, and now it's a cupboard. So bacteria and fungi will continually do that. And then the protozoa and the nematodes are there to unlock the nutrients that bacteria and fungi have just now locked up in their bodies, right? And I just want to go on a little bit of a tangent with this straw compost again, because that's relevant. We're talking about nutrient lockup versus nutrient release. It has to do with the carbon to nitrogen ratio, right? And if you ever had your straw laying about the field, doing absolutely nothing, and you have to come in and you have to fertilize your field, right? What's going to happen? Well, you're going to be adding more fertilizer because you have to decompose that straw, and microbes eat first, right? So they will basically be looking at decomposing that straw, but they will need that nitrogen. If you take that straw off, put it into a bale, and force these microbes to fix their own nitrogen, you just got rid of yourself that problem. You just saved yourself that nitrogen. So that's something to keep in mind. There's, again, just circling back to that release of nutrients. Those are the general roles of these microbes. When it comes to releasing nutrients, we could be starting looking at the actual species or groups of species. And the reason for that is I can have the entire soil food web present in the soil and still have missing nutrients. And I'll read it both on the Logon test and on SAP analysis, it just won't be there. And I'm not even talking about things like iron or zinc or manganese. I'm talking about potassium. It's still going to be locked up. And the full soil food web is there under the microscope. I've got bacteria, fungi, protozoa, nematodes. Everything is there. And it's only when we start looking at, down to species level is when we can start understanding what's going on. There is another body of work that I want to actually do that I haven't had a chance to start on that actually. There are farmers in New Zealand, for instance, who will notice that they've got a lockup of certain nutrient, that they don't have access to certain nutrient. But in that field, that nutrient's available. What can we do? Take some of that soil, and then spread it on that field. So the idea there is that, okay, well, that field is not experiencing potassium limitation. So I'm going to logically extract some of that soil, take those microbes, put them on that field. And the work that I want to actually do is to be able to make that into a tool so that you can actually use it. So this can be reliable, right? So in terms of nutrients and nutrients, availability, that's another big subject. You've got the soil food web in the soil, you've got the endophytes doing their job. You've got the mycorrhizal fungi of different types doing different things as well. And then at different times of the year as well. And then there's microbes that will work in the hot times of the year, and then there's microbes that work in the winter. It starts getting really complicated. I'm trying to just make it simple. Is there anything else that I wanted to show you? Oh yeah, buy our stuff because we need to eat. This is how you find us. If you really want to get inspired by this and you want to just start, we have done the calculations. This actually pays for itself. But if you wanted to learn this stuff to do yourself, we provide training. Next training sessions are all of November. How to make compost, how to make extracts, how to look through a microscope. You can then do your stuff yourself. We do lab work, and we produce this stuff, and nobody else has got it in the world, just us. And we swear by it. Thank you very much. Question?
So, if you're going to grow a second wheat.
Say again?
If you're going to grow a second cereal.
Yeah.
You've got chopped straw.
Yeah.
When would you use that product? How would you use it? How many times would you use it?
The most effective thing, if you were to buy this from us, the most effective time is as a seed coating. That's the most cost-effective way of using it. And if you've got that chopped straw, I would collect it, and I would bale it, and I would make it wet, and I would let it decompose for a year, and then I would use it, and I would then spread it with a back spreader as a fertilizer. We took this compost, by the way, and we wanted to test if we can actually grow stuff with it. First thing we did, it just threw us off completely. We put seeds directly in that compost. It looked perfect on paper as a soil for wheat. 10 weeks, none of them germinated. We had 3 seeds per pot and dozens of pots. None of them. I dug them out. They were completely whole. They did not decompose. They just sat there. But when I put wheat seeds into pots with soil from the field, and I calculated 175 kilograms of nitrogen per hectare, how much of that compost do I need to put in the pot? I did that. I did a control with nitram. The plants grew to the same result as the nitram side with that straw compost, and the compost side was ready a week before the nitram side. So take that straw off and start doing something with it, so that you don't have a problem then in the spring, and then, or even during the growing of your crop, you can use less fertilizer when you're doing that. Bale it up, let it rot down, and then spread it. And if you just want to start on that side, make a smaller pile, use that as a seed coating down the line. Anything else? Does that answer your question? Okay. I could tell you, buy lots of this stuff and spray, okay? But I'm not going to, because I'm not like that. I still need to eat though, so buy our stuff. Anything else?
Does the pH of the soil make a difference to how it works?
That's a very good question, and there is no definite answer. There is really no definite answer. There's plenty of research that will say that these microbes will work with the plant, and will do a lot of stuff locally, yada yada yada. I think in a mature system, that's more true. So if you wanted like first year results, correcting some pH, chemically might be an option. There is a big body of work by Dr. Olivier Husson on pH and EH, and how these things affect biology. And so this is a chicken and egg scenario, I think, bit of a thing. Anything else? Yes.
Did I hear correctly that you said the fertilizer made from the wheat straw was really only good for growing the wheat crop?
No, I did say that it fits it in terms of the benefits that you should be seeing, at least on that DNA analysis. But it still would act as a fertilizer. And so you could probably put it under your rose bush.
Okay, so could you produce fertilizer using things other than the wheat straw?
I think so. The exciting part is matching of the microbial community that seems to be providing the stress resilience to your wheat. And so there is an idea that, one hypothesis that currently Adam has proposed, again, our head geek, is that we could be making compost from the target plants only and nothing else, and see if we can replicate what we saw on those DNA tests for wheat straw for wheat. And yes?
In wood chip, what biology or anything is in that, or does it cause reaction when it's applied to the ground by the biology was on the ground?
Both. Are you talking about virgin wood going onto the soil?
Yeah.
Both.
Cut a hedge down, chip it up and chip it on the soil.
Both. Because there's endophytes in every plant. There's a very cool paper, this is actually quite recent, and just, I don't know, 3 years ago, a guy did an experiment. He took leaves that had fallen from a tree, dunked them into, that had just fallen from a tree, right? Yes? He took leaves that were sure not to be infected from the outside. Let me just put it that way, okay? And then he washed off anything that could have been outside with alcohol. So there was definitely no microbes on the surface of those leaves, right? And then he put them into sterile conditions and they still decomposed, which basically demonstrate that there are endophytes waiting dormant until those plants basically are ready to be decomposed, and they jump first. But then you do have stuff in your soil, and depending how active that is, they'll be cooperating with those. So either way, we have, in the past, we asked farmers to send us compost samples, for instance, and we've kept this leaderboard. It's quite funny, actually, Top Gear style leaderboard of compost. We're running a compost championship, by the way, right now. We're just starting one. And one of the, you may recognize the name Niles Corfield. And Niles basically sent us a sample, and he said, well, it's not my compost, it's found material. And it was very high in biology, it was very high in bacteria, very high in fungi, very good levels of amoebae, nothing else in flagellates or nematodes, really, I don't think, if I recall correctly. And so I asked him, what was it? And he said, 40-year-old wood chip. And this was a sawmill that was just chucking their waste onto one pile for 40 years. And so, sure, maybe a bird came in, deposited some microbes, and that started, decomposing. But then we see that all the time. You just put a pile of wood chip and you just let it sit wet, and it will heat up and it will decompose. Ian Tolhurst, who's a celebrated organic market gardener, solely uses compost made out of wood chip, nothing else, and just uses that as his fertilizer for all of his veggies. So everything is inside that wood chip already that you need to start going. And it seems that it's quite possible that everything you need is in the straw already. Now I think we can kickstart it, that's one thing, and I think we can also improve the conversion from the straw to nitrogen, but that's another story. That's not your question anymore. Nathan still wants to talk today.
Well, I'm just enjoying what you're saying.
Oh,
Thank you.
you're very kind.
Ever so much, it was brilliant.
Thank you. Okay, cool.
Do we have a 5-minute break while we deal with the compost camera situation? If anyone needs to go to the loo, it's literally the other side of the fire. There's still some tea and coffee and biscuits. 5 minutes. I really need to. Basically.
I was just interested in the fact that you only use a small amount of that.
Well,
Presumably you mix a certain amount of that with water and
yeah. Yeah, we actually had, Ed Galley actually used a mobile seed coating company.
Right, yeah.
So that was even easier. I'm gonna have to put this in the rose bush somewhere now.
I was going to answer rose bushes.
Uh-huh.
This is a farming scenario rather than
You can